Have you ever felt, I don't know, completely paralyzed by having just way too many choices?
Oh, absolutely. Like trying to pick something to watch on streaming.
Right. Yeah. Or imagine trying on literally every single outfit combination in your closet,
Oh, wow.
like including the ones that make absolutely no sense together, just to guarantee you find the absolute best look.
Yeah, that would take forever.
Exactly. Now, imagine a computer trying to do that, but to find the absolute best option when there are more possibilities than there are atoms in the universe.
Yeah, that's where things get really wild.
It is, and that is the world of combinatorial optimization. So, welcome to the deep dive. We're looking at a presentation from 2026 by someone going by the handle at Lex036.
Right, combinatorial optimization, from approximation classes to practical algorithms.
Yeah, and our mission today is to explore how computer scientists essentially solve the unsolvable. Because when we hit a search space of like O of n factorial or O of 2 to the n possibilities, we have a major problem.
We really do. I mean, at that scale, brute force checking every single option is just mathematically impossible.
Okay, let's unpack this. Because the modern digital world, supply chains, server routing, it relies on solving these massive problems.
Instantly, yeah. And computer scientists basically ask three fundamental questions when they face these massive, overwhelming problems.
So what's the first one?
First is feasibility. Like, does a valid solution even exist within the rules we have?
Makes sense. Just can it be done at all?
Right. Then the second is optimality. What is the absolute mathematically perfect solution? The best possible answer.
But if we're dealing with those impossible scales like the outfit analogy, finding that perfect optimality is basically a dead end, right? We literally don't have enough time in the universe.
Exactly. Which brings us to the third question, which is approximation. If we can't find the perfect answer, how close can we mathematically guarantee that we get to it?
So we just, settle for good enough? Do we just give up on finding the best answer?
Well, we don't just give up and guess blindly. We actually measure exactly how hopeless a problem is.
Hopeless in what way? Like computationally?
Yeah, we drop the problem into what are called approximation classes, moving from the easy stuff to the truly impossible.
So lay out these classes for us.
Sure. So at the manageable end, you have class P. These are problems where we can find the exact perfect answer fast.
Like in polynomial time.
Right. But then you drop into the NP hard territory, which is a lot messier. Inside that, you have a class called APX.
EPX. And these are the ones that are too hard to solve perfectly, but we can approximate them.
Exactly. We can guarantee that our answer is within a strict constant factor of the perfect answer. We sort of put a fence around our failure.
Okay, but what about the really bad ones?
That would be NPO. Those are computationally hopeless. The errors just scale infinitely. You can't even approximate them.
Wow.
And what's fascinating here is that, as the source explicitly notes, knowing the approximation class of your problem is basically half the battle.
Because it tells you what's actually possible before you waste like a decade trying to write an algorithm that the laws of physics won't allow.
Yes, exactly. It saves you from trying to solve an NPO problem.
But wait, I want to push back on this APX class for a second.
Sure, go ahead.
If a problem is in APX and we cannot mathematically calculate the perfect answer because it would take billions of years,
Yeah.
how can we guarantee that our sloppy fast answer is within a constant factor of a perfect answer that we don't even know?
Yeah, that is the paradox. How do you measure your distance from a finish line you can't see?
Exactly.
Well, we use this incredibly powerful engine called the primal dual method.
The primal dual method.
Yeah.
Okay.
It basically lets us build a mathematical floor that the perfect answer cannot possibly drop below.
And then we measure our approximation against that floor instead of the finish line.
You got it. You start by writing out your problem as an integer linear program, an ILP.
So using strict binary choices, like
Yeah.
a 0 or a 1. Buy the server, don't buy the server.
Right, but an ILP is usually NP hard. It's too rigid, so we relax it. We let those strict zeros and ones become fractions.
Okay, we let things get a little fuzzy.
Yeah, and that relaxed version is our primal problem. But the real magic happens when we generate the dual problem.
The shadow version.
Exactly. If the primal is trying to minimize our costs, the dual is trying to maximize our constraints, which we call dual variables. And crucially, no complex linear programming solver is actually needed for this.
Wait, really? No solver.
No solver. You just iteratively increase these dual variables using pure logic, and they act as a lower bound. guaranteeing our solution is at most alpha times the optimal cost.
Okay, that's a lot of abstract math. So what does this all mean? Think of it like crowdfunding.
Crowdfunding, I like that. Yeah.
Yeah, let's use the weighted vertex cover example from the source. Imagine a massive network of data pathways, those are the edges, and they connect to servers, the vertices.
Right. And each server costs money to turn on.
Exactly. You need to activate a set of servers to monitor every single pathway. But you're cheap. You want to spend the absolute minimum,
So in the primal dual method, we give a dual variable to every single pathway.
which is their budget. Every pathway has a little budget, and they all donate towards the servers they connect to.
Right. All the uncovered pathways are increasing their budgets simultaneously.
And the second those budgets hit the activation cost of a server, boom, the server pays for itself. It's fully funded.
You activate it, and now all the pathways connected to it are covered.
And the math guarantees that the total cost of these crowdfunded servers is no worse than twice the optimal cost, 2 times OPT.
Exactly. A guaranteed 2 approximation, and we never had to calculate the perfect cover.
It's just so elegant.
And it scales up, too, like with the Steiner Forest problem.
Oh, right, where you have specific pairs of active terminals scattered everywhere, and you only want to connect those specific pairs.
Yeah, leaving everything else disconnected. It's APX hard, but the primal dual method handles it beautifully using a moat interpretation.
A moat.
Like around a castle.
Yeah. Imagine the terminals are castles, and they start expanding moats outward into the graph at the exact same rate.
So they're increasing the dual variables.
Yes. And when an edge is fully absorbed by the expanding moats, it becomes tight, and we add it to our network.
And then the moats merge and keep growing until the designated partners finally connect.
Exactly. And that also cleanly yields a 2 approximation.
Okay, so that's the highly rigorous, deterministic way to do it. But then right next to this in the notes, there is a completely different approach from 1985.
Ah, Pitt's randomized algorithm.
Yes. And I have to be honest, this one kind of threw me because instead of carefully expanding moats or doing crowdfunding, Pitt just uses a biased coin flip.
Yeah, he just flips a coin to pick vertices.
But the dice are loaded, right? Like
Yeah.
if a server costs $100 and another costs $1, it picks the cheap one 99% of the time.
Right. And it picks the ridiculously expensive one 1% of the time. Wait, isn't it incredibly dangerous to rely on a literal dice roll for complex network design? I mean, what if you hit that 1% chance over and over? You'd build the most expensive network ever.
If you run it just once, yes, it's very dangerous. You could get catastrophic bad luck.
Right.
But the secret is in the expected value. Over multiple independent trials, the math works out to give a 2 approximation in expectation.
Because it easily parallelizes. Right.
Exactly. On modern GPUs, you can run millions of independent trials simultaneously. You pick the cheapest valid result, and the law of large numbers saves you.
So we just sidestepped the rigid math with pure volume. That is wild.
It really is.
Okay, so we've covered stationary networks. Let's talk about navigating them.
Yeah.
The presentation spends a lot of time on the 50-year reigning champion of this space,
The traveling salesman problem, TSP.
finding the shortest closed-loop route, visiting a set of cities, and returning home.
Right. And general TSP with arbitrary distances is NPO complete. It is completely hopeless to approximate.
Because the computer can't make logical assumptions about the distances.
Exactly. But there's a variant called metric TSP, and it enforces one rule, the triangle inequality.
Here's where it gets really interesting. Because the triangle inequality is literally just the common sense rule that taking a direct route is always shorter than taking a detour.
Taking a shortcut is faster.
Exactly. And just adding that one geometric rule demotes the problem from hopeless NPO down to APX complete,
Which unlocks the Christophides's 32 approximation from 1976.
getting us down to a guarantee of 1.5 times the perfect route.
Yeah, and Christophides did this in 6 brilliant steps. First, you create a minimum spanning tree, an MST.
Which is the cheapest backbone connecting all the cities without any closed loops. And the MST is mathematically less than the optimal cost.
Right, but an MST has dead ends. So step 2, you find all the nodes with an odd number of connections.
Because an odd number means you get stuck. You need an even number to enter and exit.
Exactly. So step 3, you make a perfect matching. You calculate the cheapest possible way to pair up all those odd degree nodes.
Which makes them all even. It cures the dead ends.
And that matching is mathematically less than or equal to 1/2 of the optimal cost.
Wow. Okay, so step 4, you combine them. You overlay the matching onto the spanning tree.
Step 5, since every node is now even, you can trace an Eulerian circuit. You can drive the whole route without getting trapped.
But you might visit the same city twice.
Which is where step 6 comes in, shortcutting. Because of the triangle inequality, if you're about to hit a city you've already seen, you just draw a straight line to the next unvisited city.
Because shortcuts are faster.
Exactly. You combine the MST, which is less than 1, and the matching, which is less than a half, and your final tour is guaranteed to be less than or equal to 1.5 times the optimal.
A 32 bound, formalized way back in 1976. But why did it take so long to figure that out? And why is an algorithm from 50 years ago still the best guarantee we have in polynomial time?
It all comes down to the bottleneck in step 3. Finding that perfect matching relies on the Blossom algorithm.
From 1965, right?
Yeah. And the Blossom algorithm operates at a complexity of O of n cubed.
Meaning if you scale up the cities, the processing time just absolutely explodes.
Exactly. No one has found a computationally faster way to guarantee that strict 32 bound without hitting that O of n cubed wall. It's dominating the space.
That is fascinating. Okay, so up to this point, we've just been settling for approximations, 2 approx, 32 approx. But what if we could get the exact perfect answer just by, like, looking at the problem's shape differently?
Now we're talking about changing the geometry.
Right, the MXCUT, where you have to partition vertices into 2 camps to maximize the edge weight crossing the divide.
In general graphs, MXCUT is firmly NP hard.
But then Hadlock comes along in 1975 with a massive structural insight.
Yes. If we connect this to the bigger picture, Hadlock realized that if the graph is planar, the whole game changes.
Planar meaning you can draw the network flat on a piece of paper without any lines crossing over each other.
Right. If it's planar, the problem drops out of NP hard and becomes polynomial. It's easy to solve exactly. He used a dual graph to turn the max cut into a min-weight perfect matching on odd faces.
Okay, wait. Let's visualize that.
Yeah.
So think of a physical map of a continent, right?
Oh.
The borders are the edges and the countries themselves are the faces. You drop a capital city in every country and draw lines between the adjacent capitals.
Exactly. You've just built the dual graph.
And Hadlock proved that finding the max city on the original map is mathematically identical to finding that perfect matching on the new dual graph.
Which we already know we can solve perfectly. He completely bypassed the NP hard wall just by exploiting planarity.
But hold on. If planarity just means drawing lines without intersections, does that mean optimizing physical road networks, which are mostly planar, they don't overlap much, is fundamentally easier for computers than optimizing abstract networks?
Yes, absolutely.
Like a highly intersected network of social media connections is physically harder for a machine to solve than a city grid.
That is the exact reason structure matters. The physical shape of the data completely dictates the boundary of computation.
That is just incredible. Okay, so to recap our journey today, we started by classifying impossibility, moving from P to NPO.
Figuring out what game we're playing.
Right. Then we saw how to use budgets and biased coin flips to approximate answers with primal dual and Pitt's algorithm.
Then the 50-year reign of Christofida's 32 rule for the traveling salesman.
And finally, Hadlock's planar magic, changing the geometry entirely. And I think the greatest takeaway for you, the listener, from this whole source is this. The other half is finding the right structure to exploit.
It's such a profound lesson.
It really is, and you can apply this to your own life. When you are faced with an overwhelming O of n factorial problem at work or in life, stop trying to brute force it. Figure out the structure, find the shortcuts, and sometimes you just have to settle for the math of good enough.
Yeah. And to leave you with one final thought based on Pitt's randomized algorithm.
Okay, let's hear it.
We use biased coin flips to approximate these incredibly complex mathematical truths, mostly because doing it deterministically is just too hard for our hardware.
Right.
It makes you wonder, could there be massive, completely unsolvable combinatorial problems in physics or in nature where the universe itself doesn't actually calculate the exact answer?
Wait, really?
Yeah. What if the universe simply flips a biased coin in aggregate just to keep functioning?
Oh, wow. So reality is just settling for an approximation. That is something to let marinate.
It definitely changes how you look at the world.
Absolutely. Well, that is all the time we have for today's deep dive.